Alright, so hello everyone. This is the lecture on 5th unit in avionics, which is communication systems. Now in this lecture, we are going to study about some of the antennas in an aircraft, and then we will study about different modulation techniques and the transceivers which are used for communication. So transceiver, it's a combination of transmitter, receiver, right? So we are going to study about all these in today's class. Now before discussing about antennas, let us have a brief overview of the working principle of an antenna. So if a wire is fed with an alternating current, some of the power will be radiated into space, right? So if you apply an alternating current to a simple wire, right, you will have some radiations around it. Okay. Now a similar wire parallel to and remote, okay, a similar wire parallel to and remote from the first one can intercept this radiated power. Okay, so if you place a second wire which is parallel to the first one and it is some distance apart, then these radiations, they can be induced into this, and because of these radiations, when they are induced into the second wire, this wire will have some current. Okay, now this current will have the same characteristics as the original current which you are applying. Okay, this is your original current and this is the induced current, right? So they both will have similar characteristic or the same characteristics. Okay, so this way we can transmit some information or some signal, right, using two wires which are remote to each other or which have some distance between each other, or wirelessly we can transmit some signal. Okay, and based on the characteristic of the induced current, we can predict the original signal. Okay, we can reconstruct or we can predict what information was sent. Okay, so this is the basis of all radio system. Okay, now this transfer of energy from one point to another happens by means of electromagnetic wave. So these radiations, they are basically your electromagnetic waves. Okay, now the electromagnetic wave, as you can see in this figure, it consists of two accelerating fields which are mutually perpendicular to each other and to the direction of propagation. Okay, so you have the electric and magnetic field which are perpendicular to each other and to the direction of propagation. Okay, so if this is your direction of propagation, then these electric and magnetic field, they will be perpendicular to each other as well as perpendicular to the direction of propagation. Okay, so this is kind of a 3D, something like this. Okay, so all of them, they will be perpendicular to each other. Now the electric field will be parallel to the direction of propagation, parallel to the wire, and the magnetic field will be at right angle to the wire. Okay. The distance between two successive peaks, it is called as the wavelength. Okay, which is represented by this Greek letter lambda. Okay. Now lambda, or the wavelength of the electromagnetic wave, is directly related to the frequency. So this wavelength and the frequency, they are interrelated, or they depend on each other. Okay, and they can be calculated by using this formula. C is equal to frequency multiplied by the wavelength, where C is the speed of light. Okay, which is 3 multiplied by 10 to the power 8 meters per second. Okay, so this is a basic working principle of an antenna, of a simple wire antenna. Okay. Now in an aircraft, we use different antennas operating at different frequencies. So the first one is your VHF antenna, that is very high frequency antennas, and they operate in the frequency range of 30 to 300 megahertz. Okay. So for an antenna to radiate in the VHF range, okay, so this VHF antenna, they are of two types. You have the dipole antenna and the unipole antenna. Okay, so first let us talk about the dipole antenna. So in the case of dipole antenna, the length of the wire or the antenna should be equal to half the wavelength. Okay, so whichever wavelength you are trying to operate, okay, and from this relation C equals to F lambda, you can calculate the frequency. Yeah, so frequency will be C divided by lambda. So whichever frequency or wavelength you are trying to emit using this dipole antenna, the length of the dipole antenna should be half of it. Okay. So for example, in this VHF range, if we are let's say willing to transmit 100 megahertz signal, okay, or if we are willing to transmit our signal at a frequency of 100 megahertz, so the wire which we will use as an antenna should be of 1.5 meters, which is quite long, 1.5 meters. Okay, so because of the long length of dipole antenna which is required to transmit the VHF frequencies, this dipole antenna is generally not used. Okay, because you would need very long length of antennas. The other type of antenna which is normally used is your unipole antenna. So in the case of unipole antenna, the length should be lambda by 4, or quarter of the wavelength. Okay, so again, if we are transmitting 100 megahertz signal, the length of unipole antenna will be around 60 centimeter long. Okay, so 60 centimeter is okay, it's not very long. Okay, so two unipole are sometimes mounted back to back to function as a dipole. Okay, so sometimes we use two unipole antennas which are mounted back to back, one below the other. Okay, or next to each other, and they together will act like a dipole antenna. Okay, so we have two unipole antennas which are mounted back to back. They together will act like a dipole antenna, and they are used for VOR navigation. So VOR, it stands for very high frequency omnidirectional receiver. Okay, so this is a type of navigation system, and we are going to study about it in the next class. Now here is a numerical example based on the formula which we have discussed. Okay, so in this example, let's read the example. So what is the length of a lambda by 4 antenna? So it is a unipole antenna for aircraft to transmit in the VHF frequency. Okay, so the question only specifies that your antenna should transmit at a VHF frequency. Now VHF frequency, it is a range of frequency. It starts from 30 to 300 megahertz, isn't it? So what we can do is we can calculate the intermediate frequency. Intermediate or central frequency, the midpoint. Okay, and try to design the antenna at that frequency. Okay, so we use the center of the communication band. So if you calculate the center of the VHF frequency band, it will come out as 127.5 megahertz. Okay, so at that frequency, or at this frequency of 127.5 megahertz, we can calculate the wavelength. Okay, so using the formula C is equal to F lambda, so you can calculate lambda. So lambda will be C divided by F. C is what? It is speed of light. So 3 multiplied by 10 to the power 8 meters per second, right? And this frequency, it is in megahertz, so don't forget to convert the units. Okay, so using this formula, if we calculate the wavelength, it comes out to be 2.35 meters. Okay, and we have to design a lambda by 4 antenna. Okay, so its length should be quarter or 1/4 of the wavelength. So 1/4 of this wavelength, it is 0.59 meters, half a meter approximately. Okay, so this should be the length of the antenna to radiate at the VHF frequency. Okay, so generally the radiation is something like, if this is your frequencies, right? So generally radiation is not at a specific frequency. It's not like you would get all the radiation at 127.5 megahertz. It's not like that. It's like a frequency spectrum. If you plot, it will be something like this. Okay, the maximum radiation will be at 127.5 megahertz, but still you will get some radiation at other frequencies also. Okay, so you get a band of radiation from the antennas. Okay, so if you are designing at an antenna at a center wavelength, then you would get some radiation within that entire frequency band. Okay, obviously it depends on different design parameter. So you could have a broad spectrum, something like this, or a very sharp spectrum, something like this. Okay, so this all depend on the designing of your antenna. Now, the next type of antenna that can be found in an aircraft is your HF antenna, or high frequency antennas. So these antennas, they radiate at a frequency range of 2 to 30 megahertz. Okay, now if we design a dipole antenna to radiate in this frequency range, its length should be around 5 to 75 meters. Okay, so if you are designing a dipole antenna, lambda by 2, if you do, you will get the length of the antenna to be between 5 and 75 meters, which is roughly the dimension of the aircraft. And if you would have guessed it, yes, we use the entire aircraft as a radiating antenna for high frequencies. Okay, so to use the entire aircraft as a radiating antenna, a notch or a slot is cut in a suitable place in the airframe, or in a suitable part of the airframe. So generally it is you cut the slot at the base of vertical stabilizer. Okay, and when a large accelerating voltage is applied through the fuselage, radiations are emitted through these notches. Okay, so when you apply very high oscillating or AC voltage, you would get some radiations from these notches. Okay, now as I was mentioning just in the previous slide, so the design or these notches, they need to be tuned, right? Their depth, their length should be accurate, right? So the notch or airframe load must be tuned. Okay, it's not like you cut a notch anywhere in the fuselage or like of any length. It should be of a specific length. It should be designed properly. Okay, it should be of specific length, depth, and all that. Right, so that is your tuning. So these notches should be tuned to correct frequency for efficient emission or efficient transmission. Okay, so without tuning, very little energy will be radiated, and you will have a large value of standing wave. Right, so radiations, standing wave, you can say, like they stand, they do not radiate. Right, so if you do not design it properly, you will have more amount of standing wave and less amount of radiation from the notches. Okay, the last type of antenna is the low frequency antenna, which operates in the frequency range of 10 to 100 kilohertz. Now for this frequency range, even the length or the dimension of the aircraft is even smaller. Okay, so we cannot use the entire body of the aircraft for as a antenna. Okay, so we use two types of antenna at this frequency. So we use something called as capacitive type antenna or loop antenna in this frequency range. Okay, so your capacitive antenna, your one plate of your so you all know about capacitors, right? So capacitor are two simple conducting plate, and in between you have some dielectric medium, right? So you have two conducting plates. Okay, and in between you have a air gap or some dielectric medium which is filled, dielectric or insulating medium. Okay, so in capacitive antenna, one of the plate of the capacitor is your airframe. If I draw the aircraft, right? So one of the plate is your airframe, and then along with that we use another horizontal tube. Okay, horizontal, you can use a horizontal tube or a vertical blade or a mesh. Okay, or a mesh kind of a thing. Okay, or even solid plate also you can use. Okay, so the aircraft causes the field to become intensified over a limited region, right? So from here you will have your radiation. So whatever radiations your aircraft is generating, it kind of like combines together in this horizontal tube or mesh or solid plate, and it concentrates all the radiation, and from the plate you have your low frequency radiations. Again, it should be designed properly. The length, the width, the thickness and everything of your plate, of your second plate which you are using, it should be designed properly to radiate within the low frequency range. Okay, so this is your capacitive antenna. The next antenna, as I mentioned, is your loop antenna. So loop antenna is basically a loop of wire, something like this. Okay, so this is your simple loop antenna. Now the field is intensified, or you concentrate more amount of radiation by using an iron core. Okay, so generally in a loop antenna we use iron core, and then we wound these wires in form of a loop around this iron core. This will uh, intensify the radiation, or this will be able to accumulate more radiation and radiate more efficiently. Okay, and sometimes two loop antennas, they are mounted at right angle. Okay, so something like this, right? So something like this. You mount two loop antenna at right angle to each other, and this will allow the radiations from all directions. Okay, so two loop antennas mounted at 90-degree or right angle to each other, and this will allow radiations in all directions. Radiation or receive or reception from all directions. Okay, so the same antenna is used for reception also, right? So you can mount two loop antennas at right angle, and this will allow radiations from all directions to be received by this loop antenna. Okay, so this loop antenna or these type of low frequency antennas, they are used for several navigation systems. For example, Omega, Lorentz, and ADF, that is automatic detection finder. Okay, so we are not going to study about Omega and Lorentz in the next class, but probably ADF we will study. Now in this slide I have mentioned the different range of frequencies and their applications in different avionic system. Okay, now in this slide I have shown the main difference between VHF and HF signal propagation. So these are the two communications or communication system we are going to consider in today's discussion. Okay, so before discussing about VHF and HF communication system, just to highlight the key difference between the two. So your VHF is mainly used for line of sight signal propagation. Line of sight signal propagation. Okay, line of sight, that means both your transmitter and receiver should be able to see each other. Okay, transmitter and receiver should be able to see each other. Okay, they should be visible to each other. Okay, so that is your line of sight communication. Now, whereas in HF communication system, you can transmit the signal across the horizon. Okay, so we all know that the earth, it has some curvature. Okay, so for line of sight communication, they should not be beyond the curvature of the earth. However, for HF communication, you can transmit to a receiver over here also, across the horizon or across the curvature of the earth. Okay, so for HF communication, what we do is we transmit the signal to the ionosphere. Okay, upward towards the ionosphere, and the signal, it propagates to the station or the receiver by consecutive reflection between the earth surface and the ionosphere. Okay, so after successive reflection between the ionosphere and the earth's surface, you would receive the signal at the ground station. Okay, so that's the key difference between your VHF and HF communication. Okay, in VHF, you are limited to line of sight signal propagation, but in HF, you can transmit across the curvature of the earth also. Okay, now using antennas, we can establish a link, a wireless link between a transmitter and a receiver. Okay, so you can send some signal using the antennas wirelessly. Okay, without any wireless connection. However, to form a useful connection or a useful link, we should be able to transmit some information using the electromagnetic waves. Okay, so to transmit some information using the electromagnetic wave, we use something called as modulation. Okay, that is, we change the characteristic of our signal, of our transmitted signal. Okay, so the waves are made to carry information by varying or changing some of its characteristics, like the amplitude or frequency. Okay, so to transmit some information, we change some of the characteristic. Mainly, we change the amplitude or the frequency of the signal. Okay, so an example of modulation is your Morse code, which was used in very old days for sending or communicating, right? So here is an example of sending SOS, that is an emergency signal or a help signal using Morse code. Okay, so basically in Morse code, corresponding to dots, you send like you turn on the transmitter for short duration. Okay, so for a dot, transmitter is on for short duration, and corresponding to dash, your transmitter is on for long duration. Okay, so that's how we send the signal. So, I mean, you have this modulation technique, but it is not suitable for transmitting complex information, something like voice in avionics. So therefore, either amplitude or frequency modulation is used. Okay, so Morse code is no longer used. We use amplitude or frequency modulation. So in amplitude modulation, the amplitude or the signal strength of the carrier wave is varied in proportion to that of the message signal. Okay, so carrier wave, it is a simple oscillating wave of constant amplitude and constant frequency. So what we do in amplitude modulation is, according to our message signal, we will change the amplitude. Okay, so we will change the amplitude of this signal according to the message signal. So you can see it here, the first one, or this is your amplitude modulation. So we can see how we are changing the amplitude of the carrier signal according to the message signal. Okay, so message signal could be anything, something like your audio signal, that is a message signal. Now, the second type of modulation is your frequency modulation. So in frequency modulation, the frequency of the carrier signal is varied or changed according to your modulating or message signal. Okay, so the second one is your frequency modulation. So according to the message signal, the frequency, you can see the frequencies there of the carrier wave is varied. And these FM modulation, it is used for radio broadcasting. You must be all listening to FM radio station, right? So that is a very good example of broadcasting. Okay. Now we have DSB-SC and SSB-SC. So these are the two amplitude modulation or transmission techniques. Let me write it properly. Transmission techniques for amplitude modulated signal transmission. Okay, so these DSB-SC and SSB-SC, they are transmission techniques for transmitting your amplitude modulated signals. So DSB-SC, it stands for double sideband suppressed carrier, and SSBSC, it stands for single sideband suppressed carrier. Okay. Now frequency spectrum. So this is the frequency spectrum of your amplitude modulated signal. So frequency spectrum in general is the range of frequencies contained by a signal. Okay. So in amplitude modulation, the frequency spectrum, it consists of your carrier frequency, omega c. Okay, we call it omega c. Then a band of frequencies less than omega c, which we call as lower sideband. Okay, lower sideband, LSB, and a band of frequency higher than this carrier frequency, or we call it as upper sideband or USB. Okay, so in amplitude modulation, the amplitude of the carrier wave is changed according to the message signal. So either you increase the amplitude or you decrease the amplitude according to the message signal. So basically we'll have either some frequencies in the amplitude modulated signal will be less than the carrier frequency and some will be higher than, because you are either adding or subtracting the modulated or the message signal. Okay, so accordingly this will be the frequency spectrum of your AM signal or amplitude modulated signal. Now the lower sideband and the upper sideband, they have the message or the information, but this carrier signal or the signal which you are getting at omega c does not carry any information, right? So generally we do not transmit omega c or carrier frequency. So carrier frequency omega c carry no information and is not transmitted. Okay. Now in the case of DSB-SC, that is double sideband suppressed carrier, the two sideband, that is your lower and upper sidebands, they are compressed and transmitted. Okay, so you compress the lower and the upper sideband and transmit both of them. So since we are transmitting two frequency bands or side bands, we require more bandwidth, okay, to transmit this DSB-SC. Okay. Now one of the advantage is that it requires low power, or it has low power consumption, but it requires a complex receiver design, right? So although this DSB-SC transmitter and receiver, they require low power for operation, but their designing is quite complex. Okay, and they are generally used for transmitting um, analog television signals. Okay, where one of the sideband, it contains the color information. Okay, so generally your television broadcasting is done using DSP SC, right? So one of the sideband, it will carry the information about the colors. Okay, and the other one will carry the actual information. Now, in the case of single sideband suppressed carrier, that is your SSB SC, only one sideband of the spectrum is transmitted. That is, either you transmit the lower or the upper sideband, right? But only one sideband is transmitted. Now in SSB SC system, a filter is used to extract the desired sideband. So we use a filter to extract one of the sideband and then we transmit. So since we are transmitting only one sideband, so the bandwidth required for transmission will be half of what you need for DSP-SC. Okay, so half the bandwidth and power is required for SSP-SC. And let's say if you need both the sideband at the receiver, generally we reconstruct the second sideband at the receiver if it is needed. Okay, so the second sideband can be reconstructed at the receiver if needed. Okay. Now in most airborne system, we have to transmit multiple information which is sent on different frequency channel, right? However, the frequencies should be equally spaced. Okay, so generally we transmit multiple information at different frequencies. Okay, but in order to avoid overlapping between the frequencies, there should be sufficient spacing between the frequencies. Okay, so for any communication like VHF, HF, you have a band of frequency, okay, or a range of frequencies, and we transmit information, multiple information on individual frequencies, okay, or range of frequencies. So to avoid overlapping, there should be some spacing. Now according to Shannon sampling theorem, a spacing of 1/2 of FM is sufficient to avoid overlapping. Okay, so where your FM is the frequency of wave on which you are transmitting your information. Okay, so the spacing should be half of that frequency minimum. Okay, and transmitting multiple information on different frequencies is called as frequency multiplexing. Okay. Now, let us now discuss about the AM communication system, that is amplitude modulated communication systems. Now, the first communication installed in aircraft were one-way system, right? That is, the pilot can only receive information. The pilot cannot transmit any information, but he or she can only receive the information relating to air traffic and weather condition. Okay. Older days it was fine because the air traffic was less, but now this is not possible, right? Just one-way communication is not possible. Now, AM is preferred for VHF and HF airborne communication, as they are proven system. Okay. Now, we have discussed about two modulations. We have discussed about amplitude modulation, that is your AM, and frequency modulation, that is your FM. So FM in general, it is better than AM, but in avionic systems we use amplitude modulation. The reason for that is we have been using amplitude modulation since quite long time, so it is being proven. So that is why it is used now also. Okay. So earlier VHF communications consists of a separate transmitter and receiver. So previously we used to have separate transmitter and receiver, but now we can use the same system for transmitting as well as receiving the signals. Okay, so they are called as transceivers, transmitter plus receiver. Okay, so now we use a single system which can transmit and receive the signal. Transmitter and receiver are combined into a single transceiver. Okay. Now, let us start with the VHF communication system. So this is your VHF transceiver. Okay. Now, the receiver portion is a conventional super heterodyne. Okay. So it is a super heterodyne system. Right. So generally we use a varactor diode or a varactor tuned RF amplifier. Right. So the purpose of this RF amplifier or RF filter is to eliminate the signal which is more than 2 times the intermediate frequency. IF stands for intermediate frequency. Okay, so your central frequency or intermediate frequency, so any signal which is not lying within the VHF range is kind of eliminated by this RF filter. fixed tune RF filter cannot be used as it mainly as it may either reject some frequencies from the desired band or admit undesired frequencies, right? So generally we do not use a fixed RF filter. That is, we do not we do not tune our filter to eliminate fixed frequencies or uh, allow only a range of frequencies. Okay, the reason for that is it may either allow some additional frequencies to pass through, or it may reject some desired frequencies. Okay, so generally the tuning of this RF filter, it is not fixed, it is variable. It depends on the value of the signal which it is receiving. Okay, so it's receiving, let's say, any signal within in this frequency range between F1 and F2. So this varactor diode or RF amplifier, it will calculate the intermediate frequency and then multiply it by 2 and filter out any signal out of this frequency range. Okay, so it is a dynamic filter, it is not a fixed filter, right? So therefore some kind of tuning is required, and that tuning is done by your RF amplifier by a varactor diode, right? So varactor diode, it kind of acts like a switch blocking any undesired frequency. Okay, uses a varactor diode for tuning. Now the received signal is amplified using a RF amplifier and sent to a mixer. So after trimming the received signal or after eliminating any undesired frequencies, it is your signal is then amplified. Okay, and it is sent to this mixer. So this mixer, it allows the receiver to scan or tune across the entire VHF band and translate the information to the individual fixed frequencies. Okay, so remember, we are transmitting multiple information at different frequencies within the VHF band. Okay, so this mixer, it will tune the entire VHF band and find out the individual frequencies, something like a radio, right? In older radios you had that tuning knob and you can scan through all the different frequencies, something like that. We do it here. Okay, now this filter or this IF filter, it will further clean the received signal at different frequencies in the VHF band, and the AM detector, it follows the IF amplifier, right? So after filtering or cleaning the individual frequencies, whatever information you are getting is then amplified and then it is sent to your detector. So this detector will convert your RF signal into audio output, right? sum of the DC component from your detector, it is sent to AGC, that is your audio gain control. Okay, and this AGC, it will control the gain of IF amplifier. IF amplifier. Okay, so some of the DC component, it is sent to the AGC, and AGC, it controls the gain of the IF amplifier. It is something similar to your voice knob. So using this DC component or using this AGC signal, you can either increase the volume or reduce the volume, kind of, right? So this AGC signal, it by adjusting the gain of the IF amplifier, you can stabilize the audio output. Okay, so it automatically adjusts the voice. Now the VHF receiver, it includes a squelch circuit. Okay, it includes a squelch circuit which removes audio from the speaker, or basically it mutes the audio when no signal is received. Okay, so it's prevent the noise of the receiver from being heard if you have no signal is received. Okay, now there are two methods for squelch. The first one is to set the AGC threshold, right? So the first method is to set a AGC threshold, and if you have any signal higher than this threshold, then your audio output will be enabled, or you will turn on the speakers. But if it is less than the AGC threshold, then your speaker will be off. Okay, so unless your received signal is more than that AGC threshold, your speaker will be off. Now this method, it has a limitation, and that limitation is, if you, let's say if you have a signal which is just below the threshold, or you may have some useful information below the AGC threshold. So if you have a fixed threshold, then you may lose that data. Okay, so we may lose some information which may be below the AGC threshold. So it is not very reliable, the first method. Now in the second method, an FM receiver is used along with your AM receiver. Okay, so in FM receiver, the noise level, it drops significantly even for a very weak signal, right? So even if your FM receiver is receiving a very weak signal, the noise or the background noise will drop significantly. Okay, you might have observed this while tuning your FM radios, right? As soon as you get some weak signal, the background noise or hissing noise, it drops significantly, right? So using the two receiver AM and FM, what we do is we compare the noise level from both the AM and FM receiver and adjust the gain of the AGC or the output of the AGC controller accordingly. Okay, so this is kind of a noise activated squelch, right? And it is quite effective, and therefore it is used in the aircraft. Okay. Now, so we have talked about the receiver VHF receivers. Now, to produce a high power VHF radio signal or to use it as a transmitter, we have to we need a carrier signal, right? And this carrier signal is generally produced by something called as your piezoelectric crystal. Electric crystal oscillator. Okay, so these are some specific materials, piezoelectric material, which produce very nice and continuous oscillation at fixed amplitude and at fixed frequency. Okay, so generally these type of oscillators, they are used to produce your carrier wave. But these piezoelectric material or these carrier waves produced, they have low power, so something like 10 milliwatt, right? So their output power is not very high, but we need high power for transmission, so that even if we have some losses during the transmission, sufficient amount of or sufficient power is received at the receiver. Okay, so what we do is we use crystal oscillators to generate our carrier wave and then increase the power of these carrier wave. Okay, so we amplify them. Now the amplification is also not done in a single stage. Instead, it is done in multiple stages, generally 2 or 3 stages, right? So 10 milliwatt carrier wave, we amplified it to 100 milliwatt at the first stage, and then we increase it to 1 watt, and then after combining it with the message signal, we again amplify it, right? So generally in 2 or 3 stages we amplify our signal. Okay, so as I have explained, you increased the power to 100 milliwatt and then to 1 watt, and then you mixed it with your message signal, or you modulate it with your message signal, and then also amplify it. So after modulation, again we amplify the signal to 10 watt, and then it is transmitted. Okay. So this is your VHF transmitter. Now let us discuss about HF communication system. Again, we will discuss about the transmitter and the receiver. Okay. So the high frequency or HF communication in the frequency range of 30 to 100 megahertz, it provides redundancy and extend the range of frequencies over which the pilots can communicate. Okay, so obviously we have the VHF communication system. So why do we need HF communication? Right, it provides an additional range of frequency over which the pilots they can communicate. Okay, now the current norm or trend is to use single sideband, okay, SSB, for high frequency communication. Okay, now for the high frequency range, the crystal filters are not sufficiently narrow to produce the channels, right? We need frequency multiplexing. So at this frequency range, or at the high frequency range, the crystals, they are not sufficiently narrow to produce the different channels which we need for multiplexing. So therefore we use low frequency signal, and then we convert them into high frequency. Okay, in HF communication we first of all use the low frequency signal and then convert it into high frequency. Now it is easier to generate single sideband at low frequency and low power, right? So again we generate the SSB signal at low power and low frequencies, and then we translate the power and frequencies to the required level. Okay, so generally for HF communication, our generation, modulation, they are done at low frequency and then we convert them into high frequencies. Okay, let's have a look as to how we do it. Okay, so this is your high frequency SSB transceiver. So your SSB signal is generated at 5.2 megahertz carrier and amplitude modulation. So your SSB signal is generated at this frequency, 5.2 megahertz, okay, at a low frequency. So the output of this balanced modulator, so at this balanced modulator we combine the audio signal with a 5.2 megahertz carrier. Okay, so carrier signal is coming from this side and your message or audio signal, it is coming from the other side, and they are both combined at the balanced modulator. So at the balanced modulator you will get a DSP SC signal. That means you will have both the lower sideband and the upper sideband after combining or after modulating your signal. Okay. Then, so this is transmitter or receiver switch. So if you are using it as a transmitter or receiver, you can switch between the two, right? So if you are using it as a receiver, your signal will go something like that. Okay. So your DSP SC signal is then sent to this block, which will remove one of the sideband. So this block, it is something like a filter, okay, and it will remove one of the sideband, either the upper or the lower. Okay, so remember, still the signal is at 5.2 megahertz. Okay, so after that, after getting your SSB SC signal, we combine it with a frequency, oscillating frequency of 80.25 megahertz using a second local oscillator, right? So the SSB signal is translated to operating frequency by heterodying the 5.2 megahertz intermediate frequency to a second intermediate frequency of 75.05 megahertz by using 80.25 megahertz local oscillator. So heterodying is a signal processing technique used to shift a signal from one frequency to another, right? So this is done by combining two frequencies as we are doing it here. So one of the frequency is 5.2 and another one is 80.25 megahertz. So we are combining it at this mixer. Okay, so mixer is generally a non-linear device, something like your transistor or diode. Okay, so you combine the two frequencies, and as a result of that, the center or the intermediate frequency of this signal will shift to 75.05 megahertz. Okay, so if you subtract 80.25 minus 5.25, you will get 75.05. Okay, so after this second local oscillator, we have shifted the frequency of our modulated signal to 75.05. Okay, by super heterodyne or shifting the frequency. Okay, so this 75.05 megahertz output is translated to operating frequency by super heterodyning it with another 78.05 megahertz. So this first local oscillator, it is 78.050 megahertz. Okay, so this signal, after passing through all that, is then translated to a higher frequency, that is 78.05 megahertz. So now my signal is in the HF range. Okay, so again you use a crystal filter, and this crystal filter will generate a frequency of 91.25, and you have a mixer here. So your 75.05 signal and the signal from your crystal filter will be mixed, and finally you will get slightly higher frequency. Okay, so the frequency synthesizer, this block itself, for example, or in this particular example, it provides an output from 78.05 to 105.0499 megahertz. Okay, so this block, or this frequency synthesizer block, it can generate different frequencies within this range, 78 to 105 megahertz at 100 hertz steps, right? So again, for frequency multiplexing, you would need to generate different frequencies within the HF band. Okay, so this frequency synthesizer, in our example, it can generate different frequency in this range and at a step of 100 hertz. Okay, so for frequency multiplexing. Okay, so using the frequency synthesizer, the signal is transmitted on the desired frequency in the HF frequency range, right? So using this synthesizer, we will transmit different information on different frequencies within this HF frequency range. Okay, so obviously you amplify it. Okay, so after this you amplify it, and then so the same antenna can be used as a transmitter or receiver. So again, you have a TR switch. So again, if you are using the antenna for transmission, you will switch or change the connection to transmitter, and then your signal will be transmitted at different frequency within your HF range. Okay, so the transmitter amplifies, the transmitter amplifier, this one, as I've explained already, the transmit amplifier amplifies the signal to the required power level, and then the band pass filter. So this band pass filter, this block, will trim the signal within the HF band before transmission. Okay. Now we can use the same block for reception. Okay, so during the reception, the same frequency conversion is done, but in reverse order. Okay, so the receiver portion of the transceiver is a double conversion super heterodyne. So again, heterodyne means you again change the frequency of your received signal. Okay, so again you would reduce the frequency to 5.2 megahertz. Okay, by following the same process but in reverse order. Okay, then to demodulate the received signal, received SSB signal, the same 5.2 megahertz frequency carrier must be used. Okay, for demodulation you have to use the same 5.2 megahertz frequency carrier. This is called as reinsertion. Now reinsertion, basically, since you are not transmitting this carrier frequency, right, so this carrier frequency has to be provided by your receiver. Okay, so since the carrier is not transmitted, the receiver must provide it, and this is called as reinsertion. Okay. Now the demodulation, it is done by multiplying the SSB signal obtained after the second local oscillator with a 5.2 megahertz signal, right? So your receiver will provide that 5.2 megahertz carrier signal, and after this stage the carrier signal is then multiplied, and then it is amplified, and then you have your detector which converts the RF or radio frequency signal into audio signal. Okay, so that is your receiver, HF receiver. So as you can see, the same block, it can be used as a transmitter and receiver, so we call them transceiver. Okay, so these were all the things that I wanted to discuss with you in today's class.